to thank the organizers for this workshop. I'm going to talk about confined grains. I'm going to describe in detail what's the geometry, and this is a work that we have been doing for some time in Chile in the group of disorder media. So this is the group, and I'm going to talk essentially a collaboration with Nicolás Mujica, who's doing the experiments, and some students, and some theoretical analysis done also in the department, and some collaborators in Chile and in Spain. But before starting my talk, I want to do an announcement. We're organizing a summer school next year in La Plata, Argentina. It's a summer school, 2 weeks, with a small workshop at the middle. And this is the web page, quite long, so you can just Google PASI La Plata and you'll find it. So send your students there. Okay. So we know that there are some problems to describe granular media, dense granular media in particular, and there's nothing yet as Navier-Stokes equation valid for a wide range of parameters. We have different regimes where we have some models, and there's several problems. For example, we know that there's large influence of fluctuations. We have shear bands. We have segregation. But I want to focus in this problem that experimentally it's hard to see what's going on inside the system. So we have to deal with observing the system on the boundaries, making some models of what's going on in the bulk, and trying to compare. So normally we don't know if the hypotheses are correct or not, etc. So I'm going to describe a geometry that in some way overcomes this difficulty, and still we can learn a lot of granular media. And this is the confined geometry. This is a shallow box. The height of the box is in between 1 and 2 diameters. So it's very thin. And we vibrate the box vertically with an acceleration that is larger than g, such that the system escapes from the bottom wall, and you get something like a fluid. And you can see that is quite easy. This is the experiments to reach stationary and dense regimes. This is seen from above. And you don't see the vertical motion, just seen from above, but particles are colliding very fast with the top and bottom walls. They have oblique collisions, and so they transfer energy from the vertical degrees of freedom to the horizontal degrees of freedom. Now that's an experiment. That's an experiment, and in the experiments we illuminate from below, and we are able to track all the particles. We lose something like one particle every 1,000 in the identification process. So the advantage of this geometry is that we can follow simultaneously the microscopic dynamics and the macro dynamics and see what's going on there. Okay, this geometry was first studied by Olafsen and Urbach and others, and the first thing that we learned that the system develops a phase transition where you have a solid coexisting with a liquid, and you can see a short movie where you see that increasing the frequency, you create a solid cluster, and we decrease again the frequency, and the cluster is going to evaporate, and you're going to have just again the fluid. Are we going to decrease there? Yes, now it's shrinking again. Yes, so it's a phase transition that the phase diagram is very rich. This is the coverage, the density, and this is the height, Actually, this is height minus 1. And you have fluid phases, fluid coexistence to 2 square layers like this. So it's 2 square layers, one on top of the other. And I'm going to place myself in this regime. So we're going to have solid and fluid phases. Okay, so the first thing that we wanted to understand is why the system separates in phases. And we know that in this system, the granular temperature evolves very fast. So it adapts itself to the density in such a way that if you increase the density, you increase dissipation, so the temperature goes down. But the pressure is a function of density and temperature, but temperature, as I said, is a decreasing function of density. So you end with an effective equation of state, pressure as a function of density, and this equation of state can be non-monotonous. So you have the phase separation from liquid to solid is just mediated by negative compressibility. Okay, what I want to describe here is I'm going to focus on this transition and to see first how to describe the dynamics, and I'm going to tell you in a minute that we can describe this transition, but besides density, we need order, local order. I'm going to explain what this is. We want to see if we can apply or not the tools of phase transitions, and yes, we can apply the tools, but non-equilibrium phase transitions. And I'm going to show that this is a critical phase transition. And finally, we want to see if there's this cluster border, you have something like surface tension, and the answer is simply yes. Okay, so I can stop here, but now I want to show you, I want to convince you that this is true. Okay, so those are the parameters of the experiments. I don't want you to remember everything, just that we're going to study 2 configurations, 1 and 2. They differ slightly on the height and differ slightly on the coverage, on the density. And we observe by naked eye that the system presented a phase transition, for example, configuration 2 at 4 and configuration 1 here. Yes, something like this. No. Okay. But we measure the density fluctuations on the system. And specifically, we measure the structural factor. And what we notice is that nothing happened with the density. Nothing special happened. So the system developed a cluster, a solid cluster, but the density fluctuations are completely insensitive to the transition here and in both configurations. We see that the density fluctuations are like this. We have a maximum and the correlation length, and this is the maximum, this is the correlation length, and nothing really funny happens there. So what we discover is that really in this transition what we have to look at is the order, local order. And as I said, the crystal is square lattice, so we measure the 4-order orientational parameter. So for each particle we identify the neighbors and we compute that. That is 1 if the system is locally square, and 0 and a small number if it is not. And we compute the global average of Q4 over all the particles. And here we see that increasing the vibration amplitude, the acceleration, something happened here in Q4 for the first configuration, and for the second configuration happens something like this, and those are snapshots increasing gamma, and you see that for the first configuration it looks like first order, that is, there's a discontinuous appearance of the cluster, and Q4 has some jumps and there's some hysteresis here, while for the second configuration, it looks like critical. So you have many tiny crystallites there that are fluctuating. Oh no.
What's the second configuration?
The second configuration was simply a bit higher. bit higher and a different density, but there's nothing really different. So this is how the system evolves. You see that the density is not really different, but the color indicates the Q4. So you have large fluctuations on Q4, but not so large fluctuations on density. So Q4 seems to be the key here. So I'm going to, this is the Q4 for C1, Q4 for C2, and in this first case, this is a discontinuous transition, and the second case is a continuous transition, and we can fit this as a linear trend plus a bifurcation with an exponent 1/2. So I'm going to focus on this case. And in this case, we now, before the transition, we measure the order fluctuations. That is, we compute the Q4 square. The Q4 square, sorry. We subtract the average value. As a function of wave vector, and we have these nice Lorentzians. So we have the destructive factor as a function of k, decays in a typical correlation length and with some amplitude. And here I'm plotting the amplitude, and the correlation length as a function to the distance to the critical point, to the transition point. And we see that both grow like power law. Okay, it's not too long, the power law, but it looks like power law. And we have fit the exponents, and the destructive factor and the correlation length have power law 1, exponent 1. Also, we were able to measure the anomalous exponent, the destructive factor in the hydrodynamic regime, and we have a non-standard exponent, 0.67, a non-classical exponent. And finally, we measured the dynamics of those fluctuations. So I showed you in the video that the Q4 was fluctuating. What I'm saying is that the fluctuations have larger and larger correlation lengths, but also they decay in time at larger and larger time scales. And this is the decay time as a function of the correlation length. And I have that the decay time of the fluctuations go like the correlation length to the power 2. So, in summary, we have measured 5 independent critical exponents: the order parameter, the amplitude of fluctuations, the correlation length, the relaxation rate, and the anomalous exponent. So everything looks like critical. So we compare with the literature what's going on there. And we notice that we have here Q4 that looks like a critical parameter, but it's non-conserved. Density that is conserved, but it's not critical, but it's key to have density, because if you decrease density, then you don't observe order. And momentum is not conserved because we have friction here. So we have just two parameters, one non-conserved and critical, one conserved non-critical, and there's a theory for that. It's called the model C. It's model C of dynamical critical phenomena, that is critical phenomena that takes place out of equilibrium. And from this theory, there are some predictions of the relations of the exponents, and we agree with that. So what I want to say is that this system out of equilibrium seems to be well described by the standard theory of non-equilibrium critical phenomena. Very shortly, want to see now what happens with the border. And the border fluctuates a lot, but we want to describe the density, the fluctuations of the border. So the distance as a function of theta minus average distance, we expand it in Fourier modes, and this is the key, if there's something like surface tension, the fluctuations of the modes should go like a constant that depends on the surface tension divided by m squared minus 1. And this is precisely that. Density amplitude of the border fluctuations as a function of m squared minus 1, and there's a nice collapse with exponent minus 1 as predicted, so we are able to extract the surface tension. So the dynamics of the border is as there's something like surface tension. And I'm not going to, because I'm running out of time, to give too much details, but the surface tension, you can estimate it just by energetics. That is the typical energy, the typical distance, and you get the correct value. And this is the final plot I want to show you. We were able to measure the surface tension as a function to the distance to the critical point, and indeed it decreases, as usual liquids. Okay, so that's my end. Thank you.
So, well, congratulations. I think it's very nice work. But the experiments are with which kind of material? You said steel?
Stainless steel, yes, 1 millimeter.
And you studied also the transition that you can see if you increase the input acceleration beyond a second critical point. I mean the evaporating transition.
No, well, we cannot go much beyond that point, let's say 6, because of you need a lot of energy in the shaker.
I know.
Yes, no, we couldn't go beyond
I
that.
suggest
That
a way of doing this without increasing too much the acceleration, and is replacing the material for another one that is more inelastic. Then you will see the evaporating. What if you express it? Then you will see that the evaporating transition is way before than 6G.
Yes, well, just let me continue with a comment about,
Because
your question is that
it will be very interesting to see.
yes, we changed some parameters, particles and the covers, and we still observe the same exponents, and this is nice because it seems that it's a universal transition.
Usually surface tension is linked to attractive forces. So do you have an idea of the physical
We have an idea
origin of the surface tension?
Yes, we have an idea of the origin. We don't have any idea of how to compute it. The origin is that inside the cluster, particles are essentially bouncing all together. They have collisions among themselves, but they are moving like this. While in the liquid part, they are just moving randomly. So one particle in the border is having different kind of collisions from the interior and from the exterior. So you have a difference of the dynamical collisions on both sides, and remember that the system is completely out of equilibrium, so if you have different dynamics on both sides, then you can have a restoring force. I don't know how to put that into numbers, especially because in experiments we cannot measure the internal collisions inside the cluster. They are too fast.
Final question?
I'm just curious, have you ever seen triangular patterns? at all?
Yes, we have seen that if you change the height. Here is the phase diagram. So you can see one triangle at smaller confinements, or two triangles, one on top of the other, if you increase the height. Yeah.
Well, let's thank the speaker once again.